this video, we're going to talk about how to test whether a particular model parameter, beta, should be included in a model or not. Okay, and so I'm going to do this using an example where I have basically insurance costs, and I'm going to use some of these variables to predict insurance cost. Okay, and this is the source of my data, which I'll include in the description of this video. Okay, and then of course I had to convert female, male to ones and zeros, and smoker, not smoker, all these categorical data to 1 and 0s. So I did that here. So right now, really all I'm concerned about is these two variables, beta, age, and BMI. And I want these two variables to predict insurance cost. Okay, so the simple model, right, would only have beta 1, only have age, right? And the full model will have both age and BMI. Okay, and sometimes you'll see this first model here, you'll see this referred to as the reduced model, right? And it makes sense because it's smaller than the full model. So this is sometimes called the full model. Okay. All right, and so basically what we're trying to test is, if you notice, the only difference between these two models is this one has beta 2 and this one does not. So we want to test whether or not beta 2 should be included in this analysis, right? Should we include beta 2 into this model, right? So what we're trying to test is HO, the null hypothesis is that beta 2 equals 0, and HA, the alternative, would be that beta 2 does not equal 0, right? And given that beta 1 is going to stay in the model, okay? So that's kind of important here. So given that beta 1 stays in the model, right? Because beta 2, it might be important if beta 1 wasn't there, right? So in the situation where, say, X1 and X2 are both doing, both explaining insurance costs in very similar way, then the presence of X1 influences the presence of X2, right? So if you have high correlation between X1 and X2, so it's very important that we are pointing out that this test is built on the idea that we are going to keep beta 1. Beta 1 is staying in the model. Okay, so to construct this test, I think it's really helpful to construct an ANOVA table, okay? And so let me go ahead and write this out. So starting with your source, then your sums of squares, then your degrees of freedom, your mean squared, and then your F statistic. Okay, so this is basically just an ANOVA table that I'm going to construct. Okay, so starting with your source, I'm going to need sums of squares regression, right, for different models. So starting with the sum of squares, the regression for the first sum of squares regression that I'm going to need is beta 1 and beta 2. So basically the full model, okay? So beta 1 and beta 2 are in this model. The sums of squares regression for the full model, that's the first thing I'm going to need. Additionally, I'm going to need the model that only has beta 1, right? The reduced model, right? Oops, beta 0, okay? So the full model and the reduced model, right? That's basically what I've just written there. And then I'm going to need to calculate the extra sum of squares, right? B2, given how much did I improve over when there was just B1 and B0, right? This is our extra sum of squares, right? So let me go ahead and write this down. So this is full, this is reduced, and then this is the extra sum of squares. Okay. Then we also need the residual. I only need the residual for the full model. Okay. And then I will have total. Total. Okay. All right. So I'm going to go ahead and need to run all these models. So let me go ahead and do that now. Next. So let me go up to data, data analysis, regression. Okay. If you have anything in there already, you might need to delete it. So let me delete everything I have in there. Okay. So Y. Click on Y, Shift Control down to highlight everything in Y. All right, let's start with the reduced model. Okay, so just X1. Shift Control down, highlighted only X1. I included labels. I'm going to call this reduced. Okay, it's going to go into a new workbook called reduced and press OK. All right. So this sum of squares regression, let me highlight it. This is the sum of squares regression for the reduced model. Okay, so when I'm here and I'm trying to fill out this table, let me go up. Sum of squares regression for the reduced model, this model that only has x1, is going to equal that guy. So let me just go ahead and press Control C, copy it, Control V. Let me paste it there. Okay. All right, the degrees of freedom for this. In general, the number of beta terms that are on the left side of this bar, that is your degrees of freedom. So just notation-wise, that's really easy. So we can see this one's going to be 1, and this one has 2 beta terms on the left side of that bar. So this one's going to be 2. Okay. It also will tell it to you here. You see it there. Okay. All right, let me go back to data. All right, so now for the full model, let's go ahead and run our regression again. Data, data analysis, regression. All right, erase what's in there in the X and then highlight X1 and not all of them. X1, X2. Okay, highlight all your data. And let's call this full. Okay, press OK. This sum of squares regression right here, home, highlight it. That's the number I want. Okay, so let's Control C, copy it. Let me go back all the way up. And Control V, paste it. All right, I'm going to delete the highlighting. Okay? Okay. So this is my sum of squares regression for the full model, my sum of squares regression for the reduced model. The extra sum of squares, remember, you always have more sum of squares regression for the bigger model, right? And the amount that you go extra is the extra sum of squares. So what you want to do is you want to take the big model's sum of squares and then minus off the small model's sum of squares. Press enter. Okay. All right, residual. This is your sum of squares residual for this is the full model. Okay, so let's go to the full model. And that's the number I want. Okay, this guy right here. So let's press Control C and then press Control V. It's a huge number. That's why it says e to the positive 11. Okay, so it's a really big number. That's okay. Okay. The degrees of freedom for this guy. If I go back to full, it tells it to me right there. So let's go ahead and copy it and paste it, right? And it should be your sample size, the number of observations that you have, minus the number of model parameters that you have. So remember, this model, this full model, has an intercept, beta 1 and beta 2. So that's 13, 38 minus 3 for 3 parameters. So you got 13, 35. Okay? All right. Mean squared. Mean squared is always going to equal the sum of squares divided by the degrees of freedom. Press enter. Equals sum of squares divided by degrees of freedom. Okay? Equals the sum of squares divided by the degrees of freedom. Okay. Great. So this guy down here, this is the mean squared error, right? Since it's your residual. So this is our mean squared error. Right? In other words, it's our estimate of s squared. Okay. Oh, I didn't calculate this guy right here. What's my degrees of freedom for this one right here? Look, I have how many parameters on the left side of this bar? Just one. So it's just one there. Okay. So equals sum of squares divided by this degrees of freedom. All right. Total. I should be able to go to any of these and get the sum of squares total. So if I go reduced or full, notice that the total sum of squares does not change. Okay, so let me go back. Doesn't matter which model I pull it off of. Let's copy it, Control C, paste it, Control V. All right, and also for the sake of completeness, your total degrees of freedom is always your sample size minus 1, so 1337. So, and for full or reduced, it should be the same. All right, so now your F statistic. How do you calculate your F statistic for this test here? F test statistic is going to equal the mean squared, okay? So your mean squared regression, okay, for this extra, right, for this guy right here. So extra sum of squares. So how much did adding beta 2 help, basically? Okay, divided by your mean squared error, right? You always divide your F statistics by your mean squared error. So it's the extra mean squared regression divided by the mean squared error. So it's equals this guy divided by this guy. All right, press enter, and there we go. That's my F statistic. So what distribution does this F statistic have? Well, assuming that, our model errors are normally distributed with mean, 0, standard deviation, constant, like homogeneous variance, and all of our assumptions are met, then this follows an F distribution, and its degrees of freedom in the numerator is 1, right here, and its degrees of freedom in the denominator is 1335. Okay, so what's the p-value associated with this F statistic? Right, so my p-value, let me just go and write it here, p-value equals, right, equals, type in equals, then f dot dist, F distribution, always right-tailed, right, and x is going to be just whatever your F statistic is. Degrees of freedom in the numerator is 1, degrees of freedom in the denominator is 1335. Close parentheses, and press enter. And you see this e to the negative 10. It's basically a really, really small number. Okay? So since it's going to be less than whatever alpha you choose, acceptable level of type 1 error, right? So since it's less than alpha, then we are going to reject our null hypothesis. Now, when we reject our null hypothesis, right, that means there is evidence to support the alternative. In other words, I know things got messed up a little bit when I was messing around with the size of the cells. Okay. In other words, though, this model here, right, it is doing a significantly better job at predicting y than this reduced model. Okay, so that's our conclusion. This full model does a significantly better job than this reduced model. Okay,